Hello, everyone, and welcome to day 2 of Mr. Saslow on leave. Let's move that down a little bit. There you go, now you can actually see me. All right, so today we're talking about free fall, which is exactly the same thing as constant accelerated motion from yesterday. It's even the exact same equations. There are two minor differences, and they're shown here on the screen. The first is that this is caused by gravity, which means that the acceleration is always going to be negative 9.8 meters per second squared, the negative meaning downwards. Now, I just told you a lie. It is not always 9.8 meters per second squared, even here on Earth. But it's close enough that we don't care. The difference in the gravitational acceleration at sea level and, say, the top of a tall mountain is there, but it's so tiny that it rounds to zero. So we're going to ignore it and pretend that the acceleration is constant everywhere on Earth, even though that's false. It's a lie good enough to be true. All right, and the second bit is that we're working in the y direction here instead of the x direction. So when we talk about displacement, instead of talking about position along a number line, we're talking about position along a number line, where usually we call 0 ground level, and then things above that. So you might also refer to it as height in some situations. But keep in mind, no matter what we're talking about, it's still position, it's still displacement. But instead of using delta x, we'll use delta y. Instead of using a, you can still use a for acceleration, but we're going to often use g. All right, and then all of those x's just turn to y's to, again, remind us that we're working in the y direction. These equations are not on your equation sheet because they're exactly the same equations as before. You just need to write them like this so that you can tell your y direction stuff from your x direction stuff, because that becomes important later. All right, short background on things, and then I'm just going to throw some problems at you and see how you do. All right, when I throw something straight up in the air, this is what its position time graph is going to look like. It has a positive displacement, a delta y that is positive. I can tell that because it starts at 0 and it ends at 125 in this case, or just shy of. All right, and now I'm going to look at the slope. Well, the slope starts positive and big, and it ends up positive and very, very tiny, approaching 0. If I look at my velocity time graph, I see exactly that. That my velocity starts positive and big and approaches 0 in a nice linear fashion, because the acceleration is negative 9.8 always. All right, so what does this mean? If I know, say, time and initial velocity, I always know acceleration. That means that I can solve for how high it's going to go, or the y displacement. And I know, I know the final y velocity, don't I? Because it's going to be 0. At the highest point, if you look at the graph, at 5 seconds, the velocity is 0. It cannot possibly go higher than that. So I know acceleration, I know final velocity by default. I then tell you one other thing, like initial velocity, and that means you can solve for the height and how much time it takes to get there. And that's it. Those are all of the numbers that we have access to, and we can find everything. Now, when something's dropped, it's the exact same story, except going in the other direction. Instead of the final velocity being 0, the initial velocity is 0. If you look at the slope, it starts at 0 and then it gets big and negative as the object falls. So my delta y here is negative 10 to 0. If I look at my velocities, oh look, the velocity graph starts at 0 and then moves, oh gosh, and then moves in the more negative direction, getting bigger and negative as we go. All right, and again, the acceleration graph, what little of it you can see because my head's in the way, is constant, negative 9.8. Yay. So here, I know initial velocity, 0. I know the acceleration is negative 9.8 meters per second squared. All right. Anything else that I know? Not by default. So I will give you one other piece of information. So let's say I tell you the time. I tell you how long this object is falling. All right, from those three pieces of information, you can solve for how far it has fallen and its speed at the end. So maybe that's Mr. Sazlo falls off a cliff. It takes him 10 seconds to reach the bottom. That's a really far fall, by the way. At that 10 seconds, you can figure out how far I've fallen and at what velocity I am slamming into the ground. The answer is a lot. All right, thrown downward. Let me back up. It looks exactly the same as when dropped, except tighter. Because I'm not starting at a velocity of 0. Look at that slope on the position graph. I'm starting at an already negative velocity. But other than that, it is identical. I'm basically just doing the second half of being dropped, is effectively what it ends up being. Delta y is still negative. Initial velocity this time is negative and probably given. And the acceleration, as always, is negative 9.8. All right, now, here's the big thing, the complete throw. What I mean by that is when I throw something straight up from ground level, it goes up and then it comes back down and hits the ground. So it starts and ends at the same position. In this case, x equals 0. Sorry, y equals 0. Well, what happens in the meantime? Well, I know that it goes up, stops for a moment, and comes back down. I know it stops for a moment because I look at the slope. The slope starts big and positive. It approaches 0 at the highest point. And then after that, it becomes small and negative. And then it gets big and negative. So if I were to look at my velocity graph, look, it's still a straight line. It's still a straight line with a negative slope, just like every velocity time graph I've shown you today. And if you look at it, it starts big positive, goes to 0 at 5 seconds, and then it ends up big and negative. If you look at the position time graph, I see the same thing. I start at a height of 0 at a time of 0. My highest point is 5 seconds when the velocity is 0. And then double that. So if my highest point is at 5 seconds, I'm going to hit the ground again at 10 seconds, at double that. All right, that was it. That was everything you need to know about free fall, except now we need to get lots of practice. This screen summarizes everything very nicely, but it's pretty simple, honestly. It's the exact same stuff that we've been doing before, but easier, because there's at least 2 pieces of information that you always know, depending on the circumstances. All right, you're done. Look over everything and then tackle those example problems.